My topic is SOC Controller for Digital Still Camera, Part 1. In SOC Controller, increasing computational demand from the application side and very deep submicron semiconductor processing from the technology side together make system on chip reality and necessary. Makers of electronic systems like cellular phone, headset, digital still camera, PDA, music player, etc. etc. Need of ASIC solution in order to differentiate themselves from the competition to increase product value and reduce cost. In SOC design system, there is a SOC design foundry. It contains wafer foundry, system houses, IP vendors, IP lab testing and packaging. We have shown here SOC design foundry. Semiconductor wafer foundry has to expand its services scope from wafer manufacturing to its services mass tooling, cell, input output library, memory compiler, and up to silicon intellectual property, that is IP, such as PLL and DAC and ADC. And there is a need to bridge the gap between electronic system houses and manufacturing foundry, wafer foundry. We call such company as a design service provider. SOC design service provider takes its input from the electronic system houses as a specification of partially designed prototype and deliver to its customer. Layout database in GDS second format, rarely for manufacturing. Close collaboration is needed among all parties in order to successfully bring a competition product to the market in line. System houses are also called electronic manufacturing services, that is EMS, because they do design and manufacturing but do not sell products under their own brands. Almost all IT products including PC, notebook, cellular phones, PDA, digital camera, music player all operated under EMS business model. EMS does not have IC design capability, instead they buy chip from IC design houses. As chip integration level increases, the room for differentiation in the board level shrinks. EMS usually command large volume in the order of tens of million units per year. It is reasonable and economically feasible for spinning their own chip. Makers of digital camera PDA use ASIC, that is all in SOC design. EMS usually does not have IC design capability. It is reasonable and economically feasible for spinning their own chip. The semiconductor manufacturing side industry is divided into three segments: wafer foundry, packaging, and testing. So in semiconductor, wafer foundry takes DDS to layout database from its customer and deliver manufacturing wafer. Wafer foundry can expand its reach of service to those who can submit GDS2 by teaming up with an SOC design service provider. For packaging and testing houses, it's beneficial to co-work with a designer service provider too. Presently, heterogeneous integration of logic, memory, and RF devices make testing and diagnosis more complicated. It is essential to involve testing houses in an SOC design project as package technology advances, subtract design, spin to pad, routing, thermal aware packages design, layout package code design. System in a package is very common to pick and associate together with RAM, DRAM, or flash in same packages. One of the approach to cope with high design complexity is reducing existing design from previous project or external sources. In IP vendors, there are microprocessor, DSP, standard interface, analog blocks, accelerator, PLL, DAC, ADC, etc. That are on external devices. In SOC control, digital camera is one of the fastest growing consumer electronic product over the past 2 years. Due to success of JPG image compression standard, advances in CMOS image sensing, and availability of high capability yet low cost flash memory card, DSC virtually taken over the traditional film based camera in just a few years. Moreover, DSC also penetrated quickly into cellular phone send, which have become the convergent target of PDA, MP3 media player, etc. etc. Ever increasing picture resolution and advanced features such as video clip recording require ultra low power and small form factor form factor of all needed functionality. Therefore, an SOC solution is very attractive to the camera makers. We described ahead SOC for DSC controller application including IP preparation, system integration and verification, chip implementation, manufacturing, failure analysis, etc. etc. Thanks.
Everyone, I will be covering a digital still camera SOC, the controllers integration with the system on chip, and various interfacing with the other drivers as well. For digital camera of high resolution, SOC is specified to include following things: a microprocessor capable of both traditional 32-bit RISC and DSP functionality, a hardwired JPEG encoding and decoding oscillator, a hardware custom logic for color image processing, a USB device controller with minimum host function and its transceiver physical interface, a dual mode SDMMC flash memory, a card host interface that we use as a card slot in our camera, an SDRAM controller interface, an LCD interface controller for viewfinder, an NTSC PAL TV signal encoder for viewing photos on TV. NTSC and PAL TV signal encoder is nothing but television display system. PAL is phase alternating line that is used in Asia and European countries, that gives us 25 frames per second with 625 lines, whereas NTSC is a national TV system committee basically used in USA and Canada, that gives 30 frames per second using 525 lines, and 10-bit video deck for TV, an 8-bit LCD deck, 2 PLLs for clock sources, 30 SDRAM macros for internal buffering. To help the development of various IPs, we built an SOC platform. There are IP cores come from multiple sources for different reasons. Each of them pose different challenges to complete the project. To help their development and to verify the functionality of each individual IP, that is intellectual properties, we built this SOC platform. In this, some IPs are existing ICs, some are soft cores that can be configured and programmed into FPGA, field programmable gate array. All IPs are interconnected together with an AMBA AHB APB on chip bus system. AMBA is advanced microprocessor bus architecture, AHB is AMBA high speed bus, and APB is AMBA advanced peripheral bus. So all controllers and drivers are connected with this bus architecture, and whole system verification is also easy due to the readiness of system level verification bench. Because most of the IPs on the platform have been proven many times in previously, for each new SOC project we only have to concentrate on verification of newly added or customized IPs. That IPs, that intellectual properties that has been customized or variably changed, or you can say newly added, we will have to concentrate on verification of only these IPs. So the whole system verification is also easy due to readiness of system level verification bench. This is a diagram of advanced microprocessor bus architecture. CPU board and extension board, all these things are connected. USB physical interface also is been done here, and ROM flash memory SRAM is connected via static memory, and USB 1.1 device controller is used here, and SD, that is also SD card used in a SD card, that is flash memory controller supplied by third party vendor. These are also these controller also specified with VHDL and RTL instead of Verilog. Mixed language simulation environment has to be set up here. During FPGA prototyping, it was performed at the time of SOC integration. And here's a dynamic memory allocation, and JPEG codec has been interconnected, and there are several blocks: audio codec, flash memory with SS, button LEDs, video and TV LCD. That will be we will be covering in the next part. The hybrid RISC implements both typical 32-bit RISC instruction set and a DSP specific instruction set in a unified instruction set architecture. To simplify a programming interface, this hybrid RISC DSP implements both typical 32-bit RISC instruction and DSP specific instruction. It was not intellectual property at all. Actually, it was a standalone processor chip used in previous generation of cameras. For software capability concern, we have to replace this with ARM or MIPS. So we can say we are currently using only ARM processor and MIPS processor instead of this hybrid RISC and DSP. We have to make it hardcore before integration with other parts of the SOC. To integrate into the SOC, simulation and test module in addition will be done to hardening the processor into high-speed hard micro. This is the block diagram of JPEG codec. Input in first in first out schedule has been accepted, and output is also as a first in first out. Register is on the top, which can receive data and read as well as write in it. So to meet processing speed requirement and long battery life, JPEG codec has to be implemented in hardware accelerator. We will be watching that one. Yes, to meet the processing speed requirement and long battery life, the JPEG codec has to be implemented in hardware accelerator. And custom logic, there is a block of custom logic for color processing functions. Color for processing function includes auto focusing, audio white balancing, color image quality enhancement, etc. It was also supplied by Maker in Verilog RTL. Need of BIST. BIST is a built-in self-test in system on chip. There are more than 30 SRAM macros used in SOC. We have jointly developed memory-based that is built-in self-test generator. This generator performs testing of 100% coverage without pattern of the testing machine. Just as I have already mentioned there, 100% testing coverage is provided by BIST built-in self-test, and that also reduces the cost of testing because testing cost is greatly reduced during production, as BIST built-in self-test generator performs 100% coverage without pattern. Verification setup is a mixture of simulation and FPGA chip co-emulation. This is the block diagram of digital camera, and we will be seeing different blocks here. So let's get first acquainted with each and every block. NFC is a near field connection. As we all know, for data transfer we use devices that have NFC near field connection in it. And NFC block is consists of HF readers. HF reader is high frequency readers, and these battery and USB voltage monitoring, status and control buttons, strobe and zoom lens positioning, these are all are controlled by microcontroller. And basically in a digital camera we use microcontroller, that is MSP 430MC microcontroller. And on the other hand, autofocus driver in digital camera, the most efficient autofocus driver is LC898122XA. You can search out these things on a website like arm.com, that is official website of ARM, and Texas Instrument, and on semiconductor.com. All the description of such drivers are available on their website. And SV driver is also used, that is most popular IC, MIC 5841. This IC is developed by using by CMOS. And timing generator consists of ultra low jitter synthesizer and cleaner. And also VCXO input, that is voltage control crystal oscillator, and VCXO input. Buttons, inductance buttons are nothing but inductance to digital converter. Here debouncer is also used. Debouncer takes the input from bouncing contact and generate clean output for digital circuits. Basically, it receives a bouncing input that is not stable and generates a clean output for digital circuit. And clocking is also used here. Clocking is a VCXO input only, voltage controlled crystal oscillator input. Audio codec is also there. There are different audio codec that can be used in a digital camera. As we are familiar with DTMF, dual tone multiple frequency, that can also be used as a audio codec. And here we can see a level shifter. Level shifter is a voltage level translation, as it implies by its name itself. And video series and DES is a serializer and deserializer, that is channel link and flat link third generation is used here. That are just video serializer and deserializer. And display power is LCD and OLED display by solutions. Here video amplifier also used, that is optional, as we connect HDMI cable just to get output into the TV or monitor, so that's optional functionality. And video amplifier is consist of basically integrated filters that will be filtering the output and to get the high resolution output on TV and monitors. And connectivity, here connectivity we have used USB. USB connectivity is very popular, and it gives ESD solutions. ESD is electrostatic discharge that occurs several times in our PCs and also in our systems. So that is just it gives ESD solutions. And USB transceiver also comes into this category only. 1394 is nothing but IEEE 1394 physical layer controllers. That is specific protocols that is provided by IEEE 1394 that comes into this block. And RS232 transceiver is basically a driver, or you can say transceiver, that is developed by so many organizations like Texas Instrument develops this transceiver, and used in computer serial ports for battery powered system to generate their own high voltage power to drive the supply voltage. So that is available from various organizations, but popular is a Texas Instrument that develops this RS232 transceiver. Here logic block consists of logic gates, voltage translators, digital and analog switches, battery management, as it implies with its name, battery charge management and other things comes into this category. And processor power is a dual channel LDO. LDO is low dropout, and AC and DC converter is used in this processor power. So this is the block diagram of all digital camera. So accordingly the controllers and ICs and drivers has been placed in this system on chip accordingly, just like it's a lens, and CCD and CMOS sensor is used here. CCD is not currently being used by manufacturers. CMOS is preferably used in nowadays. CCD is a charge coupled device, and CMOS, as we all know, a complementary metal oxide semiconductor sensor. It converts light energy, pixels light energy into electrical signal, and then process the image with the following microprocessor and embedded processor. This is optimized ARM DSC SOC block diagram. So as we have already seen the block diagram of a camera, accordingly with that functionality we implement the optimized ARM DSC system on chip, digital camera system on chip. Here video display controller is used, and nothing is new here, as we have already seen the AMBA bus architecture, advanced microprocessor bus architecture. All the things are same here, just video display controller is used here, and NTSC and PAL, as I've already mentioned the significance of this NTSC and PAL. Mali VE6 video codec is used here because most embedded GPUs do not support hardware video decoding acceleration. So video processing unit is used so many times in digital still SOC camera SOC. So this video codec is used here, and this MLI 200 GPU is a very common GPU used in digital camera SOC, and also manufactured by ARM processors, ARM technology. Image signal processor takes the raw image, and AFE is analog front end, so it receives the raw pixel input and analog front end, and accordingly performs with the interconnection with bus architecture, this advanced microprocessor bus architecture. And SATA, as we all know, serial advanced technology attachment. SATA is also a driver and also a kind of a memory. SATA driver is used to unformat or recovery of the following, recovery of so many items that we have deleted. So basically recovery of data is done by SATA drivers. And this is a USB physical interface, and all the things are familiar here. There's also one more SOC that is developed by Umbrella, that is the A7L SOC on chip ARM 1136J RISC processor. We have studied these ARM, optimized ARM, and these are actually nowadays those drivers and ARM processors are not being used, as it is Umbrella has just used this technology, recently used this technology, and as we can see, the specifications of this Umbrella SOC is much better than we have studied previously on which in the ARM processors. Umbrella is a developer of low power, high definition and ultra HD video compression and image processing products, and we will see these specification further in the accordingly with the diagrams. Here one more thing, this Umbrella, they have reduced the 25 nanometer to 32 nanometer technology. Bumped the clock rate. They actually bumped the clock rate just because to attain a low power imaging. And this is the block diagram of this Umbrella A7L SOC. And as we can see, the diagram illustrates that the three processor cores that sit in the heart of this device, image DSP, video DSP, and this ARM processor, that is 6 megahertz. Uh, a host of specific peripherals surrounds their three processor complex. To aid in the reduction of the cost and power consumption, A7L SOC can capture full 1080p video at 60 frames per second, and it can capture 16 megapixel raw images at 30 frames per second. And as I've already discussed, that it is just technology that currently being developed and used in the devices. It can also take the full HD video and click images as well simultaneously. And so there are things, image DSP and video DSP and ARM, these three plays very important role with this block diagram. And television is connected with HDMI, and all the things that are used here, we are quite familiar with this. And this is the A7L hardware platform. And Umbrella also has created a hardware development platform that includes tools, software, hardware, reference design with schematic and board layout. So this is the SOC that currently being used, and latest in the with the technology as well. So thank you very much. Now the topic is chip implementation. It is the most important process in designing the system on chip in digital camera, as it includes every fabrication process in it. So chip implementation flow from RTL to GDS to ready for tape out. RTL, as we all know, register transfer logic, to GDS2 is a stream format, and also used as a database file format in chip implementation. And GDS2 is also helpful to control integrated circuit photo masking plotting, and also it is used as a default format for transfer of IC layout data between design tools of different vendors. DSC controller count consists of 240K gates excluding memory macros. After whole system verification with hybrid emulation or simulation, it was implemented in THMC 0.25 microamp 1 IPM CMOS process packed in TFBGA 256 package. The chip implementation process has been uh, conducted by various university research process. So that is just a description of this process. It took 3 months for a team of 6 engineers to complete the netlist to GDS2 implementation. There are 30 embedded memories macros in the controller. We use in-house memory BIST, that is a built-in self-test circuit generator, to insert one common BIST controller, a multiple sequencer, and 30 pattern generators. So this is a flow of chip implementation from RTL to GDS to design flow. So here is firstly we see here SOC specs, that is specification that we have covered by different vendors, that is system on chip specifications, whereas system and hardware partitioning is very important in the chip implementation. The functionality unnecessarily assigned to hardware may result in increased cost and less extensibility. In software, it may result in underperforming design, and both can be affected by battery life. So the partitioning of functionality of hardware and software must be specified here before we initialize the process of this chip implementation. And the other thing is hardware architecture and virtual prototyping. And now we all know, and their input is provided as IP core high level model. So as we all know now, designer do not sit and code RTL in isolation to meet a proper specification and then wait for a hardware prototype before interacting with software team. Nowadays they virtual prototype the model and also interact hardware and software virtually. The virtual prototype traditionally seen as a tool for system architecture and software for software engineers. And after that, RTL coding and simulation. RTL uses different languages like Verilog and VSGL to create high-level representation of the circuit. So it is basically the RTL coding and simulation technique used in chip implementation. And here we go. Logic, DFT, and power synthesis. DFT stands for design for test, and DFT test and this power synthesis mainly use DFT compiler. Logic, whatever you can say here, but DFT compiler is the most commonly compiler used here for power synthesis. Actually, DFT compiler synopsis uh, delivers integration with design compiler and IC compiler. And whereas IC compiler is used DFT with optimization of area, power, and timing constants. DFT compiler enables designers to conduct in-depth testability analysis at RTL level to implement most effective test structure at hierarchical block level. So DFT compiler is main here, and after that physical implementation. As its name implies, physical implementation is just implementation of all such things that we have already covered in this chip implementation process. Whereas this is a pre-layout verification that is given to RTL coding and simulation, and post-layout verification is uh, that we will cover later. Here RC extraction. RC extraction it is a parasitic extraction, that is calculation of parasitic effects in both in the design devices and the required wiring interconnects of the electronic circuit. Parasitic effects that includes parasitic behavior of capacitances, resistances, and inductances. RC extraction is very important for timing analysis, circuit simulation, and signal integrity. So after that, we calculate here the delay, and that would be given to the post layout verification that we were talking about. And after that, it is DRC LVS check. LVS stands for layout versus schematic check. It is a class of electronic design automation verification that determine whether an integrated circuit corresponds to the original schematic or circuit diagram of the design. And in the end, it is here tape out. Tape out is nothing but final result of the design cycle for RC or for PCB. It is actually the final, you can say the point at which the artwork of the photo mask of a circuit is sent for manufacture. After this tape out, the process of manufacturing would be done further. And as we can see, cell memory macros, analog macros, and IP core model is included after we have proceeded for RTL coding and simulation to tape out. So this is basically a design flow from RTL to GDS to design flow. Okay. And these are the mentioned problem that occur during chip implementation. So 10 netlist changes involving echo of combinational logic, 3 echo changes to fix setup hold time violation, and 13% of pin assignments. During the course, there are three PC changes involving resynthesis and FF modification. There existed inconsistency between simulators versions among customers, IP vendors, and ourselves. Okay. Customer use PC-based Verilog modelism, while we use NC Verilog. This led to extra twists during ASIC sign-off. IP quality is less than ideal. We have to clean up many DRC LVS violation in the database provided by IP vendors. We manually performed many versions of pin assignment. The pin assignment has been performed manually many times. This happens. We perform these things manually to reduce the number of substrate layers from 4 to 2, resulting in packaging cost saving. And there is no automated tool available for this pin assignments, so we do it manually. This is the layout of DSC Controller SOC. CPU is a third party chip converter, that is, and logic JPEG codec we have already discussed, PLL, TV DAC, LCD DAC, USB foundry, flash memory, that is basically used, SDMMC, SC use flash memory, and USB DC third party. Thank
Now, our next slide is recent developments. Research and development continues to refine the lighting, optics, sensor, processing, storage, display, and software used in digital photography. Here are few examples. 3D models. First one is. Now, 3D models can be created from collection of normal images. The resulting scene can be viewed from novel viewpoint, but creating the model is very computationally intensive. An example is Microsoft Photosynth, which provides some models of famous places. Now, another one is panoramic photographs. Panoramic photographs can be created directly in camera without the need for any external processing. Some cameras features a 3D panorama too, combining shots taken with a single lens from different angle to create a sense of depth. Another one is high dynamic range cameras. Those cameras displays are commercially available now. Sensors with dynamic range in excess are also in development, and software is also available in combine multiple non-HDR image into an HDR image. Non-HDR image consists of a shots with a different exposure that will be converted into HDR images. One recent development is shown in image. Canon XS with 175 digital camera and 8 GB memory. Now, another recent development is motion blur that can be dramatically removed by a flutter shutter. Flutter shutter is nothing but a flickering shutter that adds a signature to the blur, which recognizes post-processing, but it is not yet commercially available. Another one is advanced bokeh technique, which use a hardware system of two sensors. One to take the photo as usual, while the other records depth of information. Bokeh effect and refocusing can then be applied to and directly to the image after the photo is taken. In advanced camera, that is camcorders, manipulating the sensitivity of sensor, not one but two or more neutral density filters are available. This image shows creatively positioning of camera during live view shooting, but they abandon mid and high-end DSLRs. An object specular reflection can be captured using computer controlled lights and sensor. This is needed to create attractive image of oil painting, for instance. But it is not even commercially available, but some museums are starting to use it. Another one is dust reduction system. It helps to keep dust off of the image sensor. Originally introduced only by a few cameras like Olympus DSLRs, which have now become standard in most models and brands of detachable lens cameras. But it is having another exception, such as low-end or cheap cameras. Other area of progress includes improved sensors, more powerful softwares, advanced camera processors, sometimes using more than one processor such as Canon 70 camera which has a 2-digit 4 processors. Enlarged gamut displays are there, built-in GPS and Wi-Fi, and computer controlled lighting is there. Another development consists of enhanced EDA flow and current complex SOC project which requires virtual prototyping, signal integrity test, and etc. etc. Recent development also consists of more complicated SOC testing, multimedia IP development which has already been extended, and design for manufacturability which has already been improved. Now we will come to the last point, that is conclusion. As technology becoming more advanced, we expect to see more complex SOC integration. We will see advanced video and wireless communication functions being integrated together. Another one is a mass production which has proven SOC platform including IP system, chip implementation, and another one is production methodologies which will be feasible approach to the response to the challenges.